Hey guys, so our problem definition is to create a shredder that can shred 2-inch pieces of PLA plastic waste into less than quarter-inch shreds. So as you can see, we got our full design of the shredder right here. We got the e-stop that turns the motor on and off. Motors connects to a coupling system that goes into the gearbox. The gear reducer converts our high speed into high torque, which is something we value in our shredder design. And then there's another shaft exiting the gearbox that connects to the shredder, which has teeth attached to it, and that's the actual shredding mechanism that you see. And then everything is mounted on the base plate. So our main objectives were to be efficient, safe, fully automated, be able to run continuously until someone turned it off. It's got to have structural integrity. Got to make sure we have a valid factor of safety, just so everything that made up our assembly and our shredder wouldn't fail under the applied load of the plastic. It's got to be portable and easy to store. And as far as constraints go, we had a budget, we had time we had to balance inside and outside of class, make sure everyone had a schedule that we could work around. The motor was given to us. And lastly, just facilities was a constraint because we had to make sure that the way we wanted to make the shredder, we could actually make it at Mines with everything that Mines has to offer. So in Sprint 1, we defined a problem statement, objectives and constraints, made a black box design, narrowed down ideas with a design matrix that everyone had pulled in together, made a glass box design, expected bill of materials, and initial CAD design that you can see on the right. Obviously, our final project changed a lot from the initial CAD design. We're going to talk more about that process as we go along. So Sprint 2 is really heavy with the FEA. We had to determine the correct geometry for the shaft blade and teeth. We actually had to upgrade our hex shaft to be bigger, to be a half inch, because our initial factor of safety for that initial design was 0.02, which wasn't going to cut it. So our new design hex shaft is a factor of safety of 0.4, which we felt comfortable with moving on because we modeled a worst case scenario. We calculated our gear reduction ratio that we would be needing for this project and tried to look for a gearbox that had that ratio. We submitted our first parts order form, and we updated the CAD model, as you can see on the right. So the biggest highlight of Sprint 3 that we created a 3D printed mock-up. This is the first tangible model of our shredder. We ordered our major parts, and we updated the CAD models for ease of manufacturing. So Sprint 4 is probably the hardest for our group because we fell a little bit behind schedule, but we were able to plasma cut the entire steel plate into all the components we needed. We welded the housing plates together, machined the bearing housing plates together, and assembled everything into the shredder. We just weren't able to connect the shredder to the motor and actually see it running yet, which we had expected in this sprint. So in Sprint 5, we were able to mount everything onto the base plate and orientate everything so that it would flow best with our system. And we were able to conduct our first test. So we put plastic in the shredder and ran it, and nothing actually shred. We discovered that the teeth on our blades were not sharp enough. So we took every blade off and we sharpened each tooth of each blade until we thought it was sharp enough to cut through the plastic. So we ran another test, and the results from those tests are in the videos exactly following this. So if our group were to do this again, we would design the blades to have a larger underbite and be sharper in the first place, so we wouldn't have to make them sharper again. We'd manufacture the tooth plate out of something metal that had more structural integrity, and we would manufacture the funnel to be metal too, just for a better aesthetic. So everyone in our group learned a lot about time management from this project, ordering parts efficiently in a timely manner, having the foresight to understand that things like this and a project like this has lead times with all these components that you're ordering and having to assemble and create. And those are just important takeaways that we'll be bringing into industry once we graduate.